Welcome. In this video, we will take a look at the section 2.3, looking at the derivative graphically. This is the fourth lecture in the brief calculus series. So let's start with, again, the definition of our average rate of change over an interval a to a plus h. This is where we're going to start to build our idea of the derivative at a point. So if I consider this interval a to a plus h, and we have something similar graphed below here where it's just x to x plus h, we would consider its average rate of change to be the change of the functional values, so f of a plus h, minus f of a, divided by the distance between those 2 points, and that would simply be the distance h. And we can see that kind of working out in our picture there. So this average rate of change, just as a way of review, creates the secant line slope between the points at a and a plus h. Or in general, if we wanted to just talk about it generically, the values of x and x plus h, if we were using just generic values. So let's just introduce the idea of the derivative, and then we'll kind of work with Desmos to kind of visualize what's happening here. When I define the derivative, I'm going to be defining the derivative right off of this average rate of change equation. So if we take a look at the derivative function, our derivative function is defined as the limit of this difference quotient. That's what we call that average rate of change formula. We're going to consider the derivative at the point x to be the limit as this difference quotient, as we let h go to 0, the distance in between our 2 points. We would like to get these 2 points to be infinitely close together, and so that they were really almost mimicking a tangent line. Because that's what we want in the end, is we would like a tangent line at a given point x on our graph. And here, this would be kind of the way we'd write the tangent line. This would be, again, the way we would represent the derivative at that point. So that would be our tangent line. So let's take a look at Desmos to kind of visualize what does it mean for this limit concept to kind of be in operation on this difference quotient. So let's go to a graph on Desmos. And so here we have a function in blue. This is just going to be a parabola function, 1 over 3 x squared. And we're considering what's happening at the point equal to 1. So we're going to be kind of focused on this point x equals 1 here. Currently, if we take a look at kind of the average rate of change, we can consider the slope over here with our difference quotient. Looks like currently that m slope that's calculated for us in between the 2 points that I have in purple to be about 1.6. Now let's consider again thinking about that concept of a limit where we're taking h and we're forcing that closer and closer and closer to 0. I have a little toggle here that I'm going to use to represent my h value. And so you can see me moving that around right here. Let's consider kind of moving this h quantity, that's the distance in between our 2 points, closer and closer to 0. And we'll see what's kind of happening to our slope here is that's changing, that's decreasing, it's getting less steep, that secant slope. And we're going to, again, continue to shrink this value of h, the distance in between our 2 points, closer and closer and closer and closer. I'm going to get really, really, really small. And again, this is mimicking the idea of the limit. I'm going to get them infinitely close together, right? We can't even tell that there's 2 points there, but there's really still 2 points there. So visually speaking here, it almost looks like we have a tangent line, even though we definitely don't have it quite yet. But that's what we're really trying to do here with the limit, is we're trying to force this h quantity to 0, and as that h quantity goes to 0, we're going to converge to our tangent line. And so if I can put this, the actual tangent line up there on the graph, this will actually kind of go over the graph that we have. That green line that I've just appeared here is the tangent line. And so if I kind of bring this h back and we get our secant line, as I decrease the distance in between those 2 points, that h value, notice how our tangent line is getting, or the secant line here in red is getting closer and closer and closer to that true tangent line that we're looking for. In other words, we're getting closer to that exact instantaneous rate of change at the point 1. So that's kind of just a visual of what's happening when we're actually doing the operation of taking the limit as h goes to 0. So in our next class, next lecture, we'll take a look at actually doing this algebraically, and we'll see how that works. But for now, we're going to just kind of look at the derivative in terms of a graphical lens. So let's take a look at some notation now to go along with this idea of a derivative. When we say derivative, we're thinking the instantaneous rate of change. So both of these would be the instant rate of change. And specifically, when we think about the f prime of x, that's the general derivative here. And this would kind of output for me f prime of x. This would be the instantaneous rate of change. Of the whole function of f anywhere on its domain. In other words, if I was to evaluate the f prime function, I could put something in like, for instance, f prime of 2. This would represent what's the instantaneous rate of change on the function at x equals 2. So specifically, if we look at the derivative at a single point, that's just specifically looking at what's the tangent slope at a specific point A. Again, we could plug in any value there. A is just a constant, and that would give me the instantaneous rate of change of a function, or of the function at x equals A. So we can evaluate f prime of x at any point, and A here is just kind of evaluating that general derivative, because A is just a single point. So as a little summary here, the average rate of change is found with the secant line slope between 2 points. We can say that's just really the idea of slope between 2 points. And then instantaneous rate of change is coming from a tangent line slope. And that we would call the derivative at a single point, or the derivative at x equals A. A little bit more notation that we could take a look at is just what is the derivative notation. We have some general derivative notation. We could call this f prime of x, and then our d notation, that's dy dx, the derivative of the y function with respect to x. And then we also have the notation of just y prime. If we look at those two things at a specific point, So at a point, we would have f prime of a, and then here would just be our derivative of our y function with respect to the x variable. That's our input variable at x equals a. So when we do this d notation, the y is our output, and the x is always the input variable. So our function could change its input and output variable, so we would just change that as we change our function. So let's take a look at kind of describing the derivative in a few different cases here. So we're going to let the d function, d of t, represent the distance a car has traveled on its trip to Las Vegas, where d is measured in miles and t is measured in hours. Describe the meaning of each of the following, the values below. So the first one we're taking a look at is d prime of 2. So when we consider this, again, if d, the function, is measuring distance, that would mean that d prime in general is going to be evaluating our speed or instantaneous rate of change at some time. And so when I consider these values, the input for my derivative is still going to be a time measurement, t. That's a time. And our output has to be a speed. In this case, we're measuring the miles that we go over some time measurement, and that's in hours. So miles per hour would be our output for our derivative. That would be our speed. So here we can consider the following. After 2 hours, or we can say at 2 hours into the trip, we will be driving 65 miles per hour. Again, that's going to be our instantaneous rate of change after 2 hours of driving. Let me say 2 hours. Skip the hours, 2 hours. So that's our instantaneous rate of change after 2 hours of driving. So if we clocked ourselves there, we'd be driving 65 miles per hour. Part B tells us what is our speed, in other words, at time 0. Again, that's our time in hours. And then our output would be, again, my speed, miles per hour. And we could say, if we have not traveled any way, we're starting at a stop, really. This is saying after 0 hours, in other words, we're sitting in our driveway, we will be stopped. Or going 0 miles per hour. So that would make sense that if we haven't gone anywhere, we're going 0 miles per hour when we eventually start at time 0. And then the final one looks like d prime of 3 here, similar fashion as number 2. But again, the input is still time. Our output is in speed, miles per hour. And so here we would say that after 3 hours, or at 3 hours, we will be driving at 35 miles per hour. So our speed here, at the 3 hour mark, we will be driving at 35 miles per hour at that moment. So that's not an average rate of change, it's just an instant rate of change if we were to be clocked at that speed at that hour. So the next problem we're going to consider is the idea of the derivative through a graph here again. And we're going to talk about the derivative through the lens of kind of an increasing and decreasing function. So we want to use the graph of f of x to answer the following questions. The first one is, at what input value does the graph of f of x have a horizontal tangent line? I'm going to look for horizontal tangent lines first. So if I consider a horizontal tangent line, that would be a point at which really we kind of have a peak or a valley in this graph. If I consider a horizontal tangent, one of those is just at the point 1. Notice that has a horizontal tangent line that only touches that point and glances off. We'll have a similar horizontal tangent at x equals 3. And then another one here at 4. So each of those places will have horizontal tangents, x equals 1, x equals 3, and 4. And as we go along each of these questions, I might try to tie this concept here with the derivative. So another way of saying that we have a horizontal tangent is to say that the derivative function f prime of x at 1 would be equal to 0. In other words, the derivative at 1, or the instantaneous rate of change at 1, is 0 because our slope is equal to 0. So the rate of change, or the slope here, is representing that derivative, and at 1 we would have it equal to 0. We could say in a similar fashion that f prime of 3 is also going to be equal to 0, and finally f prime of 4 would be equal to 0. So that's kind of the connection between, again, our function having a 0 or a horizontal tangent line. Our derivative at each of those individual points are also going to be 0. We can consider the next item, part B here, on what interval is f of x increasing. So if I consider where am I increasing, well, that's wherever I'm going to have really a positive slope on my graph. And so I'll highlight these in green. It looks like this first segment that we have, we could call that from negative infinity up to 1 will be increasing. And then we'll also have a segment from 3 to 4 that would also be increasing. So we can union that interval with 3 to 4. We'll notice that I'm using my parentheses here to describe these intervals because at the singular points of 1, 3, and 4, I'm actually not increasing or decreasing because I actually have a 0, a derivative equal to 0, or horizontal tangent line. So to connect these two intervals we would say is where the derivative is greater than 0. So our derivative will be greater than 0 on these two intervals because our function is increasing. Those two things are the same. The derivative is positive, or we could say that the function is increasing. Those two things would be meaning the same. The last problem would be, where are we decreasing? And so we'll have two intervals here where we're decreasing. That first interval we see is in between 1 and 3. And then we'll union that with the last interval of the function from 4 to infinity. If we considered, again, how we would describe the derivative on those two intervals, we could say that the derivative f prime of x, that same function, f prime of x, is negative on those two intervals, because we're going to have a negative slope wherever or negative tangent slope wherever we put a point on any of those intervals. So the derivative is negative, or we could say the function is decreasing over these intervals. Both would be the same. So there's where we would be positive, where we'd be negative, and where our derivative would be 0, those three cases. So let's take a look at maybe the representation of a function, its derivative, and we'll also even go into a second derivative, just to talk out what we would see in terms of the graphs. So let's start with the function and then its derivative in blue. We'll notice a couple things. One thing is kind of the turns in the graph. This is not always the case in every graph, but many times we'll notice that we have really 1, 2, 3 turns in this first graph, and then we'll have 2 turns of direction in its derivative. Just an interesting property that you might see. But let's take a look at maybe the critical points and kind of describe where those would be in its derivative. So if I looked at the places on my graph f of x where I have a horizontal tangent, I would have those at 3 points. One is in between -2 and -1. So -1 is kind of sitting right here. Another one is at 0, and then we'll have a final one, really close to, looks like 1 on this graph. So that's about 1. So x equals 1, x equals 0, and then looks like about, I don't know if you wanted to call it approximately, maybe -1.5. Around there, a little less though. So notice that the points on my function that have a 0 derivative, well, on the derivative function, we would expect those to be on the y-axis, or where the second derivative is, or first derivative here is equal to 0. So these points where we have a 0 tangent line, or horizontal tangent line with slope 0, we would expect to have y-intercept values, x-intercept values. So on this x-intercept, we notice that we have one at x equals 1, at 0, and one at, a little bit less than 1.5 or so. So at each of those points, those 3, what we'll later call critical points, are kind of representing what the graph would be on its x-intercepts, where the derivative is equal to 0. If I kind of shifted over and took a look at the derivative and its second derivative, we'll notice that we can find a few more horizontal tangent lines here. We'll have one horizontal tangent line at -1 on this graph. So this is at -1. We'll have a horizontal tangent. And here, just a little bit more than a half, approximately 1/2. Both of those will have horizontal tangents. And so when I take a derivative of this derivative, we just call that the second derivative. So this is just the derivative of f prime of x. Well, we'd expect there to be a x-intercept at both -1 and 0.5, because those are where we have a 0 tangent slope. And that's in fact what we see here at both approximately here at -1, we'll have a x-intercept, and then at over here, approximately at 0.5. There's 1 and there's 2. So that's just a property there that we want to identify, at least with our intercept values. And while we're here with these two graphs, another thing that we can notice is that where we're increasing and decreasing, I'll just do this on this pair right here. Notice that we are increasing all the way until we get to -1. So that's where our derivative graph is going to be positive. We're also increasing after we hit 0.5, and again, that's another point where we're positive. After 0.5, our derivative is positive. And then finally, in between those two turning points, we would say that we are decreasing. So we're decreasing in the interval from -1 to 1/2. That's decreasing, and therefore this portion of the graph is negative in between those 2 points. So that's another thing that we could do to identify our derivative. In a couple examples here, we'll take a look actually graphing our own derivative and kind of looking through those properties. So we're actually going to try to kind of sketch to the best of our abilities the derivative. So this is what we'd maybe call the position graph. We want to graph what we call the velocity graph or the speed graph. So we would like to go out and solve for, or sketch at least, g prime of x. So the first thing I want to do is to think about where is this g prime of x going to be equal to 0? Where are we going to have really x-intercepts on this g prime graph? So if I look at where I have horizontal tangent lines, I'm going to have one at x equals 1, another at x equals 2, and then another we'll say is approximately at 3. So really we got 3 different horizontal tangent lines. So at x equals 1, 2, and 3, we will have a derivative function equal to 0. So when I go to graph this, I know at each of these 3 points, I'm going to be equal to 0 for this derivative. So when I graph g prime of x, I know I'm going to have, I'll do this g prime function in red. I know that g prime here is going to have an x-intercept at 1, at 2, and at 3. Those are where my derivative function is literally equal to 0. So it has to be on the x axis. The next part we would want to consider is where is my derivative here going to be positive, greater than 0? Well, that would be where g of x is increasing. So we're going to consider where g of x is increasing. So that's going to be in, looks like 2 intervals. One is from 1 to 2. And another one we'll have from 3 to, we'll call it infinity, off the graph. So there's our increasing intervals. Before I maybe make a sketch with that, let me go to the decreasing intervals. I can consider where my function is decreasing next. If I consider where g prime of x is going to be less than 0, that would be where the original function, g of x, is decreasing. So when g of x is decreasing, well, it looks like I'm going to be decreasing over this first interval from negative infinity up to 1. And then I'll have a second smaller interval here from 2 to 1, or 2 to 3, excuse me. 2 to 3. So I've covered my whole graph with either increasing, decreasing, or 0 points for my derivative. And now it's time to kind of put it together. So off of this, I'll sketch this whole thing in red, but we'll go from left to right. The first interval we get is the negative infinity to 1 interval. And we said that that interval was part of the decreasing, and therefore our derivative here needs to be less than 0. And so positionally here, our derivative needs to be negative. So we're going to draw kind of a negative part of our line. Our derivative is going to be coming from below because it is decreasing. So the rate of change is going to be negative. So think of this red graph as the rate of change graph. That's really what the derivative is, that g prime. Then I'm going to have a little segment that has a increasing rate of change, and so I'm going to be positive in my rate of change. So I'm going to have a little positive part, and then I'm going to come on back down to 0 because I'm going to have a 0 tangent line there. And again, this sketch is a sketch, so it's not going to be perfect to what the derivative is, but it gives us really the shape of what we should be looking for the derivative. In the next interval, from 2 to 3, that's another interval where we are decreasing, so our derivative again needs to be negative. So to be negative means that we're going to have everything below the x-axis, we're going to be negative, and then have to come on back to 0 for that horizontal tangent at 3. And then if we take a look at our last section, this is an increasing portion of our graph. And so we're going to be positive, but it's not going to be increasing very quickly. It's going to be pretty constant. It almost looks like a line here. So our rate of change is almost going to be constant. So we'll have kind of a flatter line going to the right there. All right, so that would be our sketch derivative there. That should give us a pretty good shape of what our derivative should look like. Again, the focus here is kind of putting these points in categories. Where are we increasing, decreasing, and 0, and connecting that back to the derivative. The next question we'll consider is just ordering functional values and derivative values, because these two things are quite different. We want to make the distinction between our functional values and then the derivative values in part B. So let's see if we can rank the following quantities from least to greatest. If you want to pause the video and try yourself, you can pause the video now and we'll come back and look at it. So let's take a look at part A. We want to rank all these functional values in terms of their height. So let's go ahead and kind of fill in each of these. We have really the 0, A, B, the point at 1, it's kind of right in the middle, and then C and D. So if I consider the smallest functional value here, we would say, well, f of A is the shortest value. So we'll start with f of A. Looks like f of 0 would be next. So f of 0 is a little bit larger. And then f of B gets a little bit larger, f of 1, f of C, and then it kind of just goes in order from there. F of C, and finally f of D. Now, that was not too difficult just to see the heights of the graph. Now let's consider what if we took a look at the quantities for the derivative. So you could take a moment if you wanted to pause and look at part B. So let's consider the graph and ordering our derivative values now from least to greatest. So to do this, it might be helpful to sketch little tangent lines on the graph at each of these points. So if we consider each of these little blue tangent lines on each of the points, let's consider maybe what would be the smallest out of these. Well, this is a little tricky, but one of these values is actually a negative quantity. If we look at the functional value at f prime of 0, this is actually going to be a negative slope because it's going decreasing. So we would say that one's actually going to be negative. And so I'm going to put that as the smallest value. Will be negative there. So this is actually less than 0, so I'll just note that. If we take a look at the derivative at A, this one's pretty darn close to 0. I'm just going to kind of maybe call that equal to 0. F prime of A, that's pretty darn close to 0 itself. It's a 0 tangent line, horizontal. And if we look at the steepness of our positive points here, the last 4 are really positive in direction. The least steep out of all 4 of those remaining would probably be D. If we look at the steepness of D, it's a little bit positive, but not a ton. So we could say that's next, f prime of D, the slope there. Next would be our slope at C. We're getting more steep in the positive. F prime of 1 would be a larger slope than C. And then finally, the steepest point there is going to have the largest value for slope, the largest run for a unit of rise, and that would be the largest at f prime of B. So we'll notice that the ordering here for the functional values and the derivatives is quite a bit different. So that's what we're wanting to do. Think about what is that tangent slope going to be at each of those points, and then we've ordered them together. So as a final question, we're going to take a look at a sketch. I would call this probably a more advanced sketch, but this is going to be hopefully helpful in terms of thinking through, again, where our function is positive, negative, and where we might be equal to 0 in my derivative. So I'm going to go out and try to find f prime of A and just do a little sketch here. So first, one thing I would want to do is consider where my derivative is equal to 0. So I'll do this f prime graph in blue. Well, I'm going to have a horizontal tangent at this peak and then at this valley as well. So right off the bat, I'm going to say I'm going to have a zero derivative at both of those points, wherever they might be. There's not any values on our x-axis, so we're just going to try to sketch this freehand. A couple other things that I can notice here is that we have an increasing part of our function. I'll do this in green. So we'll do green increasing at really two parts of my function. So those two parts are increasing. And I also have this little increasing bit, but I do have a kind of a weird point, and we'll talk about this kind of like sharp edge here in just a little bit. We do have that kind of odd sharp edge. But there's really three kind of distinct little areas that are increasing. And last but not least, we'll look at the decreasing area. That would be between that maximum and the little minimum point that we have. So let's see if we can kind of start to put it together, and then we'll address that sharp point at the very end. So if I go to graph this in blue now, up until this point, I'm going to be increasing over that first interval. So that means that my graph will be increasing as well. So I'm going to be coming from the top of my graph. And again, right now, we're not going to necessarily focus on the curvature here, but we will be positive in my derivative there. In the in-between area here, between that maximum and minimum, we are decreasing, so this derivative graph needs to be negative. And so we'll have kind of a negative, or we'll be below the x-axis here for that segment. And then we'll be increasing up until kind of the x value, somewhere in here, where we have that are kind of parallel to that sharp point here. So at a sharp point, we actually do not have the ability to draw a tangent line. So we do not have a derivative. In other words, f prime of x is undefined at sharp points. And so since we're undefined at this sharp point, we're just going to do kind of a little open circle there. We're not defined at any sharp point for that derivative function. And then if we consider the last little segment of our graph, we can consider that we actually have a linear function for this rest of this graph. So this is a constant rate of change. And so the derivative graph should be constant whenever we have a linear function. So this slope doesn't look super steep. So we don't know really a value to put this on because we don't have a scale here, but just any constant line shouldn't be too high, but this is going to be constant, again, constant derivative where we have a linear function. So this is going to give you a good kind of starter shape for this function. And so that whole blue graph is the derivative. So thanks for watching. We will take a look at kind of algebraic derivatives in our next lecture. We'll take a look at the definition of the derivative and work it out algebraically, and we'll also take a look at some derivative rules. So thanks for watching, and I hope to see you in the next video.